NEC Electronics. This is a video on ISRO Scientist Electronic Post preparation, and from today we are going to start the syllabus wise preparation of ISRO Scientist Electronic Post, and today we are going to see some questions from the control system subject, which is the first subject included in the syllabus of the Scientist Electronic Post, and we'll be seeing some of the questions. Okay, and also I just want to inform you that we have been created a separate playlist for digital signal processing English and digital signal processing Malayalam. And I am doing videos continuously on the playlist of digital signal processing English because I've been receiving a lot of comments to do the DSP videos in English. Just wanted to inform you that there is a lot of videos included in the separate playlist created for DSP English. So if you want to watch any videos on DSP, please do watch that playlist. Okay, so the first question is, negative feedback in a closed loop control system does not dash. A. Reduces the overall gain. B. Reduces the bandwidth. C. Improves disturbance rejection. D. Reduce sensitivity to parameter variation. Now, if you see the control systems, there is a closed loop control systems. Basically, there are two types of closed loop control systems, that are the closed loop control system with positive feedback and closed loop control system with negative feedback. Now today, or in this question, we are talking about the closed loop control system with negative feedback. Even though I'll be explaining to you what are the basics of this positive feedback closed loop control system and negative feedback closed loop control system. So if you see a positive feedback closed loop control system, means there is a system and there is a feedback connected to the input. Okay, so this is the output, let it be Y. This is the input X, and there is a feedback with some gain. Okay, so if the system is a positive feedback closed loop control system, means this feedback is being added to the input, and this addition is happening in phase. So there is an in-phase addition happening in a positive feedback control system, and as the result, what is happening is the overall gain of the system will get improved. So the original there is an original gain of the system, and the overall gain will be higher than that of the original gain. So that is the advantage of a positive feedback control system. And in the case of a negative feedback system, means the reverse is happening. So there is an input X, there is a system here, and there is an output, and there is a feedback with some gain, or there is a feedback in general, and this is being subtracted from your original input or your input, and this is happening out of phase. There is out of phase subtraction is happening, or the signal will be subtracted out of phase from your original input X. So that is happening in a negative feedback control system. That is a closed loop control system. And due to this subtraction, what will happen? Obviously, the gain has to reduce, right? So the gain, that is the overall gain of the system, will get reduced due to this negative feedback that is being added. Okay, due to this negative feedback added, the overall gain will get reduced. So that is the case with the negative feedback closed loop control system. But you have to remember one thing, that even though the gain will get reduced, the bandwidth will increase to cope up with this reduction. That is, the gain, bandwidth, product will be the same. Even though the gain is reducing, the bandwidth is increasing, and hence the gain, bandwidth, product is same. So this thing you have to keep in mind. So these are the basics of a positive feedback control system and a negative feedback control system. This is one of the very basics of control systems. In a positive feedback control system, the signals are added with the feedback. In a negative feedback control system, the signal is being subtracted from all the signals, that the feedback and the input is being subtracted out of phase. And as a result, in a positive feedback control system, the gain is improved. Here the gain will get diminished, but the gain, bandwidth, product will remain the same. Now let us see what are the options. Negative feedback in a closed loop control system does not dash reduces the overall gain. No, it reduces the overall gain. It is a correct option, right? So this is not your answer because the gain is reduced. Option B, reduces the bandwidth. It is the wrong option because just now I told that what will happen? The bandwidth has to improve in order to maintain the gain bandwidth product as same, because the gain is reducing or diminishing. So the bandwidth has to improve. So this is a wrong option. Now option C, I'll just check. Improves disturbance rejection. Yes, this actually the negative feedback is added to reduce the disturbance in the coming from the input. So that is happening in a negative feedback control system. So your option C is also right. Option D is reduce sensitivity to parameter variation. This is also right. Actually, this negative feedback will reduce or avoid the variation in the inputs. So from the four option, the wrong option we have to choose, that is does not. So the wrong option here is option B, which explains that your bandwidth is reduced. But actually what is happening? Your bandwidth is improving or increasing to maintain the gain bandwidth product as same. So the correct answer for this question is option B. Okay. The next question which we are going to discuss is this. A causal system having transfer function h of s equal to 1 by s plus 2 is excited with 10 u of t. The time at which the output reaches 99% of its steady state value is dash. Option A 2.3, option B 4.3, option C 2.8, option D none of this. Now you are given some values. Let's just try to draw a small figure from this. Okay, you are given a causal system's transfer function. So the transfer function of a system is given, which is 1 by s plus 2, right? So this is given and this is represented using h of s. Now you are given some input because the system is excited using a input 10 u of t. I'm going to call it using the letter x of t, and I'll have some output, right? I'm going to call it by y of t. Now this is a transfer function. This is an input signal and there is an output signal. The time at which the output, which is a y of t, reaches the 99% the steady state value. So in order to calculate the steady state value, first we need to find what is the output, right? Only then we can obtain the steady state value of the output. So first let us try to find what is the output, which is a y of t. So here we are given h of s and we have x of t. Now what is x of s? That is the Laplace. This is given in Laplace, right? So Laplace transform of 10 u of t will be your x of s, right? So that is 10 by, this is a unit function, so 10 by s will be your Laplace transform or your x of s. Now you have your x of s is 10s. You have your h of s as 1 by s plus 2. Now what will be your y of s? I'm going to remove this. I'll write it above. That is your x of s is 10 by s and your h of s is 1 by s plus 2. Then y of s equal to h of s, that is a transfer function, into your input or x of s, right? So that is h of s is 1 by s plus 2 into 10 by s, right? So this is your y of s or your output function. Now this is the Laplace transform. We need to find the 99% of the steady state value. That is, we need to find the time. We need to find what? Time. So time is obtained by, we need to find the inverse of this. Only then we will get time. Is there any time quantity here? No, right? So first we need to find the inverse Laplace of your y of s, which is your output function. I'll remove these things. I hope it is clear. Okay, I'll remove these things and I'm going to find my inverse Laplace of y of s because I need to find the time point. Okay, so L inverse of this is 10 by S into S plus 2. Okay. Okay. So in order to make this little more simpler, or in order to find the Laplace inverse more easily, what I'm going to do is I'm going to split my numerator. So numerator is what? 10. So if you split it, 5 by S minus 5 by S plus 2 will be your, this function is the same as this function, because if you solve this you will get this 10 by S into S plus 2 itself. So Laplace inverse of is your what? Y of t. So I'm taking this 5 is common, then L inverse of 1 by S minus 1 by S plus 2. Now what is the Laplace inverse of 1 by S? It is 1. Okay, so 1 minus, what is the Laplace inverse of 1 by S plus 2? It is e raised to minus 2t. I hope the Laplace transform is clear to everyone. So this is minus e raised to minus 2t. So this is your what? This is your output function in terms of time. Now we need to find the steady state value of this output function. Now this is your output in terms of time. Okay, I'll just remove these things and I'll write it above now to make a little more space. That is your y of t equal to 5 into 1 minus e raised to minus 2t. Okay, now at the steady state what will happen? The function will be steady or constant. Okay, so the function will be not having the time variable at the steady state, or it will be some constant, or we can say at steady state the value of the function y of t at steady state, it will be when this e raised to term will not be there, or it is a constant value. So the value will be equal to 5. Okay, so the steady state value of this function is 5, and we have to find the time when the output reaches 99% of the steady state value. So what is the 99% of the steady state value? First find that. Steady state value is 5. 99% means 99 by 100 into 5 is your 99% of the steady state value. And we need to find at what time this value is achieved, means we have to equate this y of t with this and find the time parameter. We need to find the value of this t, and for that we are equating the original function y of t with the 99% of its steady state value, which is here. Now solve this. 0.99 equal to 1 minus e raised to minus 2t. 1 minus 0.99 is 0.01, right? So e raised to minus 2t is 0.01. Okay. Now I'm going to take the logarithm, anti-logarithm of this. That is, we'll get minus 2t equal to e raised to, means you have to take the natural logarithm or ln of 0.1. If you take the logarithm, natural logarithm of 0.01, it will be minus 4.6. If you solve it now, you will get the answer. So it is minus 4.6. Here there is a minus 2t. This 2 and this will get cancelled and it is minus 2.3, and this minus and minus also get cancelled, and you will get the time value as t equal to 2.3 is your time period when the output function reaches the 99% of its steady state value. So the correct answer for this question is your option A, which is 2.3 seconds. And one more thing, I forgot to tell that all these values are given in seconds, right? So the correct answer is t equal to 2.3 seconds is your answer, which is your option A. The next question we are going to discuss is this. If the closed loop transfer function of a control system is given as T of s equal to s minus 5 by s plus 2 into s plus 3, then it's a dash. A, an unstable system. B, a minimum phase system. C, a non-minimum phase system. D, none of this. So they are asking what type of a system is the given system. We have to find from the transfer function. Now, in order to answer this question, you should understand some things first. So here we are given what the transfer function, right? So if you see the transfer function T of s minus 5 by s plus 2 into s plus 3. This transfer function is having a numerator and a denominator, right? If you equate the numerator with 0, you will get some values of s or some roots, and that roots are called zeros. And if you equate the denominator with 0, or if you find the roots of the denominator, you will get poles. Now this poles and zeros actually determine what type of the system is a given system. And we draw a S-plane. Since it is given in the Laplace transform, we draw a S-plane and locate these poles and zeros to see whether the system is stable or not. Okay, so this system is having a left hand side and a right hand side. The right hand side is the positive side. This is a simple coordinate system, and the right hand side is positive like all other coordinate systems, and the left hand side is considered to be negative. And if the poles lie on the positive side, it is said to be the unstable system. That is, if the poles are lying on the right hand side, the system is unstable. And if the poles are lying on the left hand side, means the system is stable. So the first option is an unstable system, right? So in order to make the system unstable, or in order for the system to be unstable, the poles should lie on which plane? It should come on this plane. So first let us check whether the system is unstable or not. Okay, so what I'm going to do is I'm going to equate my denominator with 0. So if equating the denominators to 0 means s plus 2 equal to 0, or s equal to minus 2. Again, s plus 3 equal to 0 means s equal to minus 3, right? So s equal to minus 2 and s equal to minus 3, both the values are negative, or coming in which plane? Left hand side. So it is here and here. Let this be minus 2 and let this be minus 3. Then the poles are on which half of the plane? Left half of the plane. So is the system stable? Yes, the system is stable because both the poles are negative. So the option A is not right, because the system is not a unstable system. So just cut off this option A. Now what is given the option B? Option B is a minimum phase system. Option C is also related to the option B, a non-minimum phase system. So for answering this option B or option C, that is to check whether option B or C is the right answer, you should know what is a minimum phase system and what is a non-minimum phase system. Okay, so a system is said to be minimum phase if the system and its inverse are causal and also stable. I'm going to remove these things because we have found that the poles are on which side of the plane? On the left side of the plane. Now I'm going to check whether the system is minimum phase or not. So as I said, a minimum phase system means the system and its inverse are 1. Causal, 2. Stable. Okay, so we have already talked about what is stability. Stability is actually understood from the position or the location of the poles. Now what is a causal system? So a causal system is a system in which the output depends on the present and the past inputs. Okay, I'll draw a system here. So this is a system. This is the output. Okay. This is the input x of t. Okay, so the output of the system, let this be h of s, the transfer function is h of s. So the output of the system, it is y of t, depends on the current input and the previous or the past inputs only, not on the future inputs. Such a system is called a causal system. So while you are studying the control systems, the causal term is seen everywhere. So you should be familiar with this term, causality or causal system. So we represent the causal systems are the y of t, or say y of t0, depends on x of t for t should be less than or equal to t0. Okay, so till t0 or less than t0, the values of t or the values of x of t is taken, and after t0 or the future inputs are not taken by the system or the output is not affected by the future inputs, means such a system is called a causal system. I hope the concept is really clear. And if the system and its inverse are causal and stable, means the system is having a minimum phase. So such systems are called minimum phase systems. And if the condition is not satisfied, that is if the system and its inverse is not causal or not stable, means the systems are not minimum phase systems. Okay. So how to check whether the system is having a minimum phase or a non-minimum phase? It is by observing the zeros. Okay. So the numerator, if we equate, we will get the zeros, right? So I'm going to check what is the zero of the system. So the numerator is s minus 5, and if you equate it to 0, you will get s equal to 5. So s equal to 5 is your zero value, and it lies on which half of the plane? It is on the right hand side or on the positive side. So it is, let us assume this is the value 5. So this is your zero value. Okay. So we say that stability lies in this half of the plane and non-stability is on this half of the plane. So the zero is not stable. So the system is not stable in terms of the minimum phase. So by looking at the zero, we can find whether the system is having minimum phase or non-minimum phase. So if the zeros are lying on the stable half of the plane, then the system is having minimum phase. If the zeros are on the positive coordinate or the positive side of the S plane, means the system is having non-minimum phase. So for this question, since we are having a positive value of 0, the system is having non-minimum phase, and the correct answer for this question is your option C. Since the zero value is positive, it's having a non-minimum phase. So this is how you check whether the system is having minimum phase or non-minimum phase, by observing the zero values. And how will you get the zero values? It is by equating your numerator with 0 or finding the roots of your numerator. Okay. So these are the questions which I have included in this video. So we have talked in this video about control system questions, and while discussing each question, we'll be discussing all the terms associated with that question or the basics of that question, whichever is needed. So we'll be doing videos on such a basis. Okay. So I really hope this is useful for your ISRO exam preparation. If yes, please do like this video and also share this video with all your friends who's preparing for ISRO examinations. And also don't forget to subscribe to the channel. Thanks for watching and keep on watching.